Pluto is a distant and befuddling minor planet, once a singular individual from our planetary family. Anyway, later upsetting announcements by driving astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a dumbfounding disclosure. They recommended that this cool world is on a crash course with Neptune. Yet, how might this at any point happen, and what might be the results of such a basic event? Are we seeing an enchanting, gaudy, precious event, or is there another thing to this approaching limitless effect? Go along with us as we research the potential consequences of a Pluto-Neptune impact. Pluto, a past planet that was downsized to a dwarf planet, is vital in light of its odd circle, and it remains a subject of interest and study in the galactic community, as shown by late suppositions by leading specialists. Pluto's circle is hazardously near Neptune's, and Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potential dangerous crash between these two planets, which would represent a huge risk to Earth. How is such an event even possible? Pluto's excursion around the Sun is not normal for that of some other planet in our nearby planetary group. It requires a complex 248 years to finish a solitary circle, which means that since its discovery in 1930, it hasn't even completed one full revolution yet. Anyway, the interest doesn't stop there. Pluto's circle is marked by its unprecedented bowed shape, straying significantly from the practically round circles of the major planets. What makes Pluto's circle even more astonishing is its tendency of 17 degrees to the ecliptic plane. The course Pluto follows is essentially more extreme compared to other planets. One of the most intriguing parts of Pluto's circle is its convergence with Neptune's. For something like 20 years in each circle, Pluto actually draws nearer to the Sun than Neptune, challenging what we'd expect from their situations in the planetary system. This prompts the normal inquiry: why hasn't Pluto rammed into Neptune? The response lies in the gravitational effects of different planets. The investigation of Pluto's circle began not long after its discovery. Initially, stargazers attempted to determine its exceptional circle. Dissimilar to other planets whose circles lie near the ecliptic plane, Pluto's circle stood apart with its precarious tendency and bowed shape. The secret extended with the acknowledgement that Pluto's circle in all actuality does, without a doubt, cross Neptune's. The stability of Pluto's circle, notwithstanding these intricacies, is evidence of the complexities of heavenly mechanics. The three-body issue in space is about sorting out how three bodies, like Pluto, Neptune, and the Sun, move and influence each other through their gravity. Pluto's circle is, as a matter of fact, turbulent. Minor deviations in starting circumstances can lead to tremendous contrasts over significant stretches. Anyway, these astonishing properties of Pluto's circle have been found to maintain stability over especially significant timeframe scales, keeping tumult within proper limits. Late recreations have assisted us with figuring out how the giant planets, like Neptune, Jupiter, and Saturn, influence Pluto's circle around the Sun. Jupiter's monstrous gravity is strong enough to keep Pluto on a steady way for possibly billions of years. These factors are essential in keeping everything under control, as well as consistency in divine mechanics. Without these elements, our nearby planetary system would be a position of far more significant tumult and capriciousness. Pluto's circle is a striking portrayal of divine mechanics at play, showing both stability and strife within our neighborhood planetary system. The interesting attributes of its circle, impacted by the gravitational powers of adjacent planets, especially Neptune, highlight the complicated and dynamic nature of space. Predicting huge events, particularly at the point when it involves turbulent circles like Pluto, presents enormous challenges. The inherent unusualness of these systems means that long-term forecasts are often filled with uncertainty, while numerical simulations offer a solid means for understanding and predicting the future behavior of heavenly bodies. They too highlight the limitations of our predictive abilities. So, for what reason are conspicuous astrophysicists just now raising concerns about an expected crash between Pluto and Neptune? Notwithstanding the different complex forces working to prevent such an event, Neil deGrasse Tyson and Michio Kaku, both famous cosmologists, have expressed concern about a possible impact between Pluto and Neptune. If Pluto and Neptune were to collide, it would be a spellbinding and horrendous event in our nearby planetary system. The impact would release a tremendous amount of energy, probably obliterating Pluto because of its smaller size and frigid composition. Debris from the impact could disperse across the planetary system, potentially introducing a risk to other planets and their moons. For Neptune, such an impact could change its current climate and possibly its circle, contingent upon the specifics of the accident. Michio Kaku, a prominent theoretical physicist known for his work in string theory, brings an interesting perspective to the discussion. His views on the future of space exploration and the connection between heavenly mechanics and theoretical physics offer valuable insights into the mysteries of significant phenomena like Pluto's circle. Figuring out the complex gravitational interactions and orbital mechanics of heavenly bodies like Pluto can yield critical information for future space missions. This data can help in navigating the planetary system more effectively, predicting potential risks, and even planning missions to the outer reaches of our planetary system and beyond. The lessons gained from studying Pluto's circle can be applied to exploring other heavenly bodies, providing a roadmap for how we could approach and understand distant worlds in terms of planetary science. Heavenly mechanics and theoretical physics are profoundly interconnected. The movements and interactions of planets, including the gravitational dance between Pluto and Neptune, relate to the major principles of physics. If Pluto and Neptune were to collide, it would be a fantastic event in space science, offering an extraordinary observational opportunity that could even connect with string theory. String theory, a hypothetical framework where the point-like particles of particle physics are replaced by one-dimensional strings, aims to explain the fundamental forces and matter in the universe. The impact could create extreme conditions of energy and gravity, potentially leading to states where predictions made by string theory could become detectable. For example, the high-energy impact could offer insights into the behavior of fundamental particles and forces under extreme conditions, a key area of interest in string theory. While the direct effect on Earth would be negligible due to our distance from the outer solar system, the scientific implications of such an event could be significant, potentially contributing to our understanding of the essential. Raised concerns about a possible impact between Pluto and Neptune, shedding light on the complex forces at play in our divine neighborhood. Their alerts underscore the importance of understanding the gravitational interactions and orbital mechanics that govern the movements of heavenly bodies. Pluto's circle, characterized by its volatility and steep inclination, challenges traditional assumptions and redefines our perspective on planetary motion. Unlike the nearly round orbits of its neighboring planets, Pluto's path follows a unique course, crossing with Neptune's orbit at points during its long journey around the Sun. The gravitational influence of other planets, particularly Neptune, plays a crucial role in shaping Pluto's orbit and maintaining its stability over many years. Despite the wild nature of its path, mathematical simulations and theoretical models play a fundamental role in predicting the future behaviors of heavenly bodies and understanding the intricate interactions between planets. These simulations show that while Pluto's orbit is tumultuous over centuries, it remains relatively stable within the broader context of the solar system's gravitational field. The potential for a crash between Pluto and Neptune, as proposed by astrophysicists Neil deGrasse Tyson and Michio Kaku, highlights the ongoing uncertainties and unpredictability in planetary dynamics. While such an event remains speculative and highly improbable in the near term, the gravitational dance between Pluto and Neptune underscores the delicate balance of forces that govern heavenly bodies within our planetary system. Beyond its scientific significance, the study of Pluto offers practical insights for future space exploration missions. NASA's New Horizons spacecraft, launched in 2006, provided amazing pictures and data of Pluto and its moons during its historic flyby in 2015. The mission revealed stunning detail about Pluto's surface features, including mountains of water ice and vast fields of frozen nitrogen, enhancing our understanding of the land processes shaping the distant dwarf planet. The success of New Horizons mission highlighted the technological advancements and collaborative efforts required for deep space exploration. By studying Pluto and its moons, scientists gained valuable insights into the variety of heavenly bodies and the environmental conditions present in the outer regions of the solar system. These discoveries have implications for future missions to explore other dwarf planets and transneptunian objects, helping us understand planetary formation and evolution. Pluto's status as a dwarf planet has also sparked discussions about the criteria used to classify heavenly bodies within the planetary system. The debate over planetary classification reflects broader questions about scientific categorization systems and the evolving nature of astronomical knowledge. While Pluto meets several criteria for planetary status, such as orbiting the Sun and having sufficient mass for self-gravity, its classification as a dwarf planet highlights the diversity of heavenly bodies beyond the traditional planets. Studying Pluto's orbit expands our knowledge of heavenly mechanics and planetary dynamics to the outer reaches of the solar system. By examining the interactions between Pluto, Neptune, and other heavenly bodies, researchers can gain further insights into the evolution and development of planetary systems. These insights are crucial for developing theories about the origins of our solar system and understanding the processes that shape planetary bodies over billions of years. Pluto's discovery and subsequent study have contributed to our understanding of planetary motion and the development of the Kuiper Belt, an area beyond Neptune populated by small icy bodies. Studying Pluto's orbit provides clues about the gravitational interactions that may have influenced the formation of planets during the early stages of the solar system's development. Understanding the complexities of heavenly mechanics can also inform future space exploration missions, including the search for habitable worlds beyond our solar system. By studying the movements of distant heavenly bodies, astronomers can identify potential targets for future exploration and assess the feasibility of traveling to other star systems. The potential impact of a Pluto-Neptune collision, while highly improbable, serves as a reminder of the dynamic nature of the universe and the unpredictability of large-scale events. As we continue to explore the outer reaches of the solar system and beyond, the study of planetary orbits and heavenly mechanics will remain a central focus for astronomers and space agencies alike. Pluto's orbit, which deviates significantly from the paths of other planets, offers valuable lessons about the intricacies of planetary motion. The stability of its orbit over long timescales, despite its volatility, provides important insights into the balance of forces that govern the movements of heavenly bodies. In a sense, the ongoing study of Pluto's orbit and its potential interactions with Neptune reflects the broader challenges of understanding the universe at large. With each new discovery and each theoretical model, we continue to refine our understanding of the universe, unveiling the mysteries of distant worlds. As we venture further into the mysteries of Pluto and its orbit, it is essential to consider the broader implications of studying such a distant heavenly body. Pluto's orbit offers more than just insights into its own peculiar path. It serves as a fundamental case study for understanding the behavior of objects on the edges of our solar system. Its position and interactions with Neptune highlight the importance of gravitational forces that extend beyond our immediate planetary neighbors. These studies contribute to a better understanding of the Kuiper Belt, a region filled with icy objects that may hold clues to the early solar system's formation. One captivating aspect of Pluto's relationship with Neptune is the resonance between their orbits. Despite their paths crossing, gravitational forces have prevented a collision by locking them into a stable orbital resonance. This resonance ensures that the two planets never collide, even though their orbits intersect at certain points. This system of orbital resonance is not unique to Pluto and Neptune, but it highlights the delicate balance of forces that govern planetary motion in the outer solar system. Such interactions serve as a reminder of the complex gravitational dances that occur between distant bodies, making the study of such phenomena essential for predicting future changes in our solar system. Additionally, the study of Pluto's orbit could also shed light on the behavior of similar dwarf planets and transneptunian objects found even farther in the solar system. These distant bodies may hold important clues to understanding the processes that led to the formation of the solar system. By studying their orbits and the forces that shape them, astronomers can gather valuable data to inform models of planetary system evolution. The potential for future missions to the outer solar system is enhanced by our understanding of Pluto and its dynamics. The success of the New Horizons mission to Pluto opened up new avenues for exploring these distant regions. As we plan missions to explore other Kuiper Belt objects or distant exoplanets, the knowledge gained from Pluto's study will undoubtedly guide our strategies and technological advancements.